Welcome to software security. Unfortunately, I think it looks like this room has no room microphone, so you all need to be very quiet, otherwise it will probably be very hard to hear me. So there is no microphone here. A few general things. I'm Eric. I am an assistant professor here in Twente, and I am teaching software security here in Twente for the first time. And what are we going to do is that we will have 4 lectures about different topics. And we will have 3 to 4 lab sessions. Currently, we have only 7 appointments in the roster. I will try to get another lab session for the final week. So we will very likely have 4 lectures and 4 lab sessions. And what we will do in this course is 4 different things. So we will talk about low-level programming languages and their respective security problems, which means bugs that you can create in C. Then we will talk about a solution for that, which is a more secure language, which is called Rust. So C is there like for eternity. And, well, there have been alternatives suggested to C. And Rust is not the first alternative to C, but it seems to be the first language that could be a good alternative to C that is becoming widely adopted. So in the second part of that lecture, we will talk about Rust and the advantages of Rust compared to C, and how you can create much safer code in Rust than you can do that in C. In the third part, we will talk about automated tools that detect bugs in C. So in C, you can create certain types of bugs. And there are advanced tools that give you quite a good chance to detect those bugs. And we will talk about that in the third part of the lecture. And the final part is software security in your development process, which means mostly web security. So there we will leave the world of C, go a little bit to the world of high-level languages, and look at the security problems that you find in those languages. The rules for the course: there will be assignments, and you will work in teams of 2. There will be grades for the assignments, which are either just not sufficient, sufficient, or excellent. You should aim for an excellent. So excellent is the best grade you can get. And in general, getting an excellent will be very hard. There might be optional or bonus parts in the assignments, and to get an excellent, you should solve those bonus parts just to get a sufficient, while you just do the normal assignments. And for not sufficient, you do nothing at all. To get admitted to the exam, you should have at least 3 times sufficient or better. So you can get 1 non-sufficient for your assignments. You can still participate in the exam, but when you get not sufficient for 2 or more assignments, then you cannot participate in the exam and you did not pass the course. And when you get an excellent, that gives you a 0.5 bonus for the exam. That means when you get 90 points in the exam, well, 90 out of 100, and you have 2 assignments that were rated with excellent, then you get 100 points in the exam. So it gives you 0.5 grade, well, 0.5 bonus on the grade of your final mark in the course. But you need to pass the exam with at least half of the points to pass the course at all without the bonus. So when you get 45 points in the exam, but you have a bonus of like 1, so that you don't get a 5.5, no, you haven't passed the course. So first thing is the materials. So I will publish materials on Canvas. Canvas is our learning platform that we will use for the course. And I will also publish the lecture recordings here, so that will be recorded. Another reason for you is to be quiet while I'm speaking, because otherwise you are on the recording with something that's not supposed to be public, and that's a very good microphone here. And we will use the GitLab server that's hosted by the SNT. So there is a website, gitlab.snt.utwente.nl. You can go there, and you can sign up with your student account, and then you can use that server, and we will use that server during the course. And there is a book called Software Security. We may or we may not use the course. So there is a website called Slido, and you will use that website to collect feedback during my lectures. So what you should now do is you should now go to that website. and it will ask you for a code, and that code will be Tango 242. And the first question that I have for you is, shall we use the book for the lecture, or should we rather use other teaching material? Before you make a decision, there are good reasons to use the book. The good thing about the book is there you get like everything in a comprehensive view. So the book is a book just about software security. Each chapter uses the same terms, everything is explained in the same way, which is a good thing about the book. The bad thing is the book is now about 10 years old, and things have changed a bit in that the while. So I know that, okay, so I mean there are certain types of students. Some really love to learn with a book, because the book always uses the same terminology. You have like one central resource where you can look up things. And on the other hand, I can also provide you with a lot of online articles. The good thing about the online articles is I will almost always use state-of-the-art online articles. But for a few topics, it's kind of interesting to look at historic stuff. So for example, when you're wondering, okay, why is C as it is? Then it might be wise to look at an article like that's 30 years old that explains how C was created. But otherwise, I will try to use as modern teaching material as possible so that you get like a very up-to-date view on the topic of software security. Only problem with that is each author of such an article might use slightly different terms, a slightly more or less advanced language. It's written for a more or less a well-educated audience, sometimes for managers, sometimes for programmers. That always changes a bit, but the good thing is you always have like state-of-the-art material. And it looks like you prefer online article slides and other material. So I will not focus the lecture so much on the book. Of course, when you are a big fan of learning from books, you can still get the book. But when you do not get the book, it will not be a problem for you. So we will try to stick to online articles. And the website that you're just using, you can keep that open, because you can also ask questions there while I'm lecturing. The good thing is you can ask those questions anonymously, and also when I'm teaching something, I can finish the current slide. And sometimes, well, you would like to ask a question that's already answered in the next 2-3 slides, so we'll then just skip that question and continue with the slides. So while that thing is not showing a poll, you can use that to submit questions there. Okay, thanks for the feedback. So the course is based on the course from the previous year. So last year, Jacob van der Poel gave the course. He's not in Twente anymore, so I'm now taking over the course. But don't worry, I've taught secure programming before with a slightly different focus. But also Jacob didn't invent the course, and instead it's based on a course from the University of Maryland and a course from Eric Pohl from Radboud University. I think he's now in Nijmegen. So it's not entirely my topic what I have here, but it's based on the idea of a lot of other people. And of course I will add more teaching material, and then the content will slightly advance. So what are we talking about today? We are talking about software security in general. Software security means that you usually write a program for a more or less specific purpose. So for example, there is currently PowerPoint. That's a program for delivering, content to slides. And in probably every more or less significant program, significant complex program, there are bugs in the code that will cause the program to behave different than expected. And some of those bugs might be misused to make people do something what they are not allowed to do. So that might be something like you get access to the solutions for the assignments. That might mean that I get access about your data that I'm not supposed to have access to, things like that. And that is what we are trying to prevent in that course. And in general, that is hard for a very simple reason. You, as a programmer, write software for a specific purpose. So I tell you, I need programs that will do something. And then you start programming, and you will deliver a result. And in general, I will be happy with your result when your program does what I want it to do, what I told you before, when it meets the requirements. And I will be very happy when it does that very fast, when it has a nice looking user interface, and also when it supports many devices, like my tablet computer here, my laptop computer here, and that small computer I have here. But security is hardly visible. So in general, when you deliver an insecure solution, I will not immediately see it. When you deliver a slow solution, I will complain. When you deliver a solution that has a crappy user interface and have actually no idea how to use it, I will also complain. But when it's insecure, then probably quite for a while I will not find it out, and I will not complain, but I will complain later when I find it out. And when we talk about software security, then we need to fix a specific set of terms. So when you program something, you don't do something wrong in your code, then we call that a weakness. Or not necessarily something wrong, but when you do something in a way that is not optimal, so when there are better solutions how to do it. So when you have code that is maybe very ugly, very hard to read, or that does things in a kind of unstable way, then that's a weakness in your code. And when I can use that weakness for an attack, then it's called a vulnerability. It means when there is something wrong in your code and I can use that to do something I'm not supposed to do, then it's a vulnerability. And when I write software that exploits that vulnerability, we call that piece of software an exploit. So an exploit is a program that I run that will then in general use another program locally or through a network connection and will make that program do something what's not supposed to do, so that I get more things to do than I'm actually allowed to do. And when the programmer fixes that weakness or vulnerability in the code, we call that a patch. So that patch might be either delivered in source code form or it might be delivered in binary form. So when you release a new version of your program that has that vulnerability fixed, then that's a patch. And when an exploit is published for a vulnerability for which the vendor hasn't released a patch yet, we call it a 0-day. So 0-day is an exploit without a corresponding patch, which means it will work against pretty much everything. So because you have no chance to patch that. And in your code, there might be different types of flaws. So for example, there could be design flaws, which means that, well, usually when you try to build a software program, you come up with a design first. Design might be something like a class diagram or something similar where you just structure your piece of software, but for a more complex project, you might have a design that involves several things like several components, a network protocol, a user interface, a backend, maybe operational strategy, backup and restore procedure, something like that. So a design for a software program might be arbitrarily complex or it might be quite simple. And sometimes when you have a bad design for your software, then that might be a flaw by itself. So for example, when you design a network protocol and that network protocol, you forgot about encryption. So you can see all the data that's traveling through the network connection. That's a design flaw. Then I can attack that successfully. Or it might be not a bug in the design, but it might be a bug in your implementation, in your code. So then it can be either in the code itself, or it can be a problem with interaction with the environment your code is running in. So for example, have you ever heard about an SQL injection? Who never heard about an SQL injection? Raise your hands, please. No one? Fine. So an SQL injection is a typical example of a problem that arises from the interaction with the environment. So when you try to send an SQL query to an SQL server, and when your program is vulnerable to SQL injection, then that query might be altered. and then I can run attacks against your program. And, well, those flaws are not just there, and when somebody finds it gets fixed, there is now an actual market for those flaws in code. So, for example, there is a company that promises you to pay, well, that promises to pay anyone money for when he finds bugs in popular programs. So, for example, on the top we have iPhone remote jailbreak with persistent 0-click, which means when you find a bug in the iPhone, so that you can send something to an iPhone, which will trigger a vulnerability there, which allows you to run code on that iPhone to persist that code, which means like install an app with high privileges on that iPhone without requiring the user to click on something. So when you, for example, manage to build a malicious website, when that website is visited with an iPhone, and then it triggers a vulnerability in the iPhone and, for example, in the iPhone browser, and then, yeah, a new app is installed on the iPhone with high privileges, and that's iPhone remote jailbreak with persistence, and 0-click means that no interaction from the user is required. Then you get $1.5 million US. So those are the prices that are currently being paid for bugs in popular operating systems. And for other things, so for example, when you find a bug in the Facebook Messenger that allows you to take over your conversation partner's phone, then you get just $500,000 US. And yeah, when the iPhone exploit requires some interaction by the user, like to confirm something or something like that, or to click on a specific icon, then that's just 1 million. So there is now a market out there for vulnerabilities in popular software programs, so you should really do something to avoid them. And that is what we will do in the course. In general, there are 10 things you can do to avoid bugs in your code. So whenever you write code, the first thing what you do is you validate your input. It means whenever you get data from somewhere, you try to make sure that it's correct, that it's properly formatted, that it contains the information you wanted. So for example, when you expect a positive integer and you read an integer from somewhere, you check that's actually a positive integer and it's not negative. The next thing what you do is you listen to compiler warnings and also to the warnings of your runtime environment. So when you compile your code, your compiler might generate warnings, and very often that warning is a very good indicator for insecure or broken code. So whenever you get a warning, you listen to them, listen to it. You design your code for security policies. That means when you do the design of your application, and very often then you will split your application into different modules and components, and maybe a client and a server side and something in between. And very often you will find out that just a very small part of your application needs to run with high privileges. And another part of your application doesn't need high privileges. What you then do is then you try to extract the code that runs with high privileges, and you try to put it into a separate module, so that you only have a very little bit of code running with high privileges, and all the other code can be running with low privileges. Low privileges can mean you're not running as root on Linux, but instead you're running under a normal user account. For web applications, it can mean something else, that a certain part of your web application is not allowed to run JavaScript in the client's browser. Another part of your web application is allowed to do that. Or it could mean completely different things. So for example, also for Android, you could actually try to split your app into 2 permissions. One app has high privileges, the other app does not, and they are communicating through a defined channel. Next thing is what helps very often is keep it simple. So when you write code, try to make it simple, try to make it easy to read, because that helps you to discover security relevant bugs in your code. The next thing is default to deny, which means whenever you make a decision in your code that's security relevant, the default for that decision is deny. Which means, for example, when you validate your input, and you might have a certain list of characters that you're expecting. So for example, when the input is a name, there are certain characters that are not supposed to be in that name. For example, a quotation mark. And when you try to validate the input, you can do that in two ways. Number one is you have a blacklist, so you have a list of bad characters that are not supposed to be in your input, let's say a quotation mark or a backtick or something like that, or $sign. And then you have like a bad list of characters, which is called a blacklist, and then you compare your input to the blacklist, and when it contains a character from the blacklist, then you reject it. A much better approach is when you have a whitelist, which means that you have a list of characters that might appear in a name. And then you check your input and check whether all those characters are in that whitelist. And when you encounter a character that's not in the whitelist, you reject the input, which means the default is actually reject. And only when the input just contains whitelisted characters, then it's accepted. The next thing is called least privilege. So you try to run every piece of code you have with the least privilege possible. Least privilege can mean a lot. So for a Linux, that could, for example, mean it's just running as a normal user. And then there are many more features you can use on Linux to actually restrict the privileges of your code. So for example, there are capabilities on Linux. Nowadays, there is something called seccomp. There are namespaces on Linux. There's a change root environment, and there are many more ways how to drop privileges on Linux. So you can try to make your code run with the least privilege possible. The next thing is sanitize your output. So whenever you pass something on to another component in your system, you make sure that what you pass on is properly sanitized. That it contains only what you want to print, that you make sure it doesn't have any invalid characters, that all values are within the expected ranges, and that everything is properly escaped and encoded. The next thing is defense in depth. Defense in depth means that when you write a program that runs with kind of modular design, or when you build an IT system that, of course, has kind of modular design, then you make sure, just in case one part of your system breaks, there is still a second line in defense. That could mean, for example, that you configure, when you run a computer network, you have like an internal and an external network, that you configure all services in the internal network to accept only connections from internal IP address ranges. And you configure your firewall not to let anything through from the outside to your internal services. Which means when the configuration of your internal services is wrong, and it will accept actually connections from the outside world, it's still blocked by the firewall. On the other hand, when the firewall is maybe misconfigured or it fails, then an attacker still cannot access internal services, because those internal services will only accept connections from internal IP addresses. So you try to build your system always in a way that there are at least two lines of defense. And the next thing is you can try to adopt a secure coding standard, so you can try to modify your development environment and your way of writing code in a way that it will always prioritize security, and security will always be checked in the development process. And there are certain ways how to do that. For example, the first step in software security is actually do nothing, so you don't care about it. And the next thing is when somebody reports a vulnerability, then you release patches, and you do that regularly. Another thing what you can do is you can test your software manually for security relevant weaknesses and bugs. Even better is when you have automated testing. For example, you have static analysis while you're writing software, and while you're developing that software, it's automatically tested by some kind of static analysis tool. And by the way, when I always say static analysis tool, nowadays effectively a compiler is some kind of very weak static analysis tool. So very often a modern compiler, at least a modern C compiler, will try to check your software, and it will try to report things that could be a problem. So every time when I say static analysis tool, of course there are dedicated static analysis tools for security, but a compiler is also some kind of static analysis tool. So compiler is like a very basic static analysis tool. You can also train your programmers for security. So you can send them to a secure programming course, and you can then educate them and tell them how secure code needs to look like. More advanced thing is you can use dynamic analysis tools to check your code. So you can actually run your code with certain inputs and then see how your code performs. And very often you see certain problems only during runtime. So static analysis tools are tools that just look at the code and how it's compiled, but they do not run the code. And they are able to spot certain weaknesses, but not all. And dynamic analysis tools, well, at least they spot other weaknesses than the static analysis tools. So some things are easy to spot for static analysis tools. Other things are easy to spot for dynamic analysis tools. The general disadvantage of dynamic analysis tools are that they are slower. So dynamic analysis tools require your code to run. And of course, which parts of your codes are running depends on the input. So you need a lot of different inputs that will hopefully trigger all possible code passes in your code. And depending on how well those inputs are, certain misbehaviors of your code might be exposed or might not be exposed. So in general, dynamic analysis tools, they take longer. And another thing is you can make security part of your design. So when you start designing a program, you're trying to split that up into modules, components, whatever, you can already start thinking about security. So that helps you to prevent design issues, because very often when you have a problem in your design, it's very hard to fix. So you might need to update your network protocol, and that's very hard. On the other hand, when you have something like an SQL injection, your code that's in general very easy to fix. But changing the network protocol might have a lot of consequences. So we will now go through various examples of weak C programs. And before you do that, I would like to ask you something, which is did you actually learn about security when you start learning C? And by the way, who of you is not able to do C programming at the moment? 2, 3. By the way, who of you learned C programming with me as part of your operating systems course? Okay, very few. So it looks like roughly 1 out of 10 of you have actually had a proper security training when they started learning C. And a third of you had apparently no training in security at all when you started to learn C. And just imagine what it would mean when you would say, okay, well, apparently a third of the people on the street who are driving a car have never had an education about how to safely drive a car. So that's one of the reasons why security is still hard today, because a lot of people, when they start learning about programming, they do not learn about security. Maybe another thing is, in which language do you like to implement your web apps in? Because for the last part of your course, it is we will play a little bit around with web applications. And we still need to pick a language for that. And it looks like Python and Java are quite popular. So we will try to make the last part of the course based on Python and Java. Okay. But for now, for the next section, we continue in C, and then we will continue in Rust. So, I have some example C code here, and you try to spot the bugs in the code. What is wrong here? So what could go wrong? What? Amount. No, it's an integer. Well, you can say, okay, we are saying, okay, amount is the amount of money in cents, so then we say integers are fine. Okay, what else is wrong?
I was going to say amount can be negative.
Yes, amount can be negative. So there is no check whether the amount is negative. And when you put a negative amount, then the code probably doesn't want what you want it to do.
There is potential for overflow. Int is a bounded.
Yes. So int may actually overflow, which means when you put a very large value for whatever, then a number might overflow in C. Or might also underflow. So what else is wrong in the code? Yes. So we have a check here. Balance is lower or equal to the amount, but that's not correct that way. So instead of checking for lower or equal, we should rather check for higher or equal. Yeah, so you can actually have a lot of bugs in your code. And those bugs are partially specific to C, partially they happen in other languages as well. So for example, we have a logic bug here, C check, which is greater or equal. That can happen in pretty much any language. Then we have overflow issues. That happens in some languages. So some languages have overflowing integers, others do not. Yeah.
Can we assume that this thing runs on multiple threads because then there is also a concurrency problem?
Well, yes, you might also have a concurrency problem depending on whether that thing is running single-threaded or multi-threaded. And yep.
Shouldn't balance be initialized before?
Balance. Apparently, it's not initialized when it's declared, but it's probably initialized later. So what you see here is not an entire program, but instead those are certain methods. So there might be code next to them that's not visible on the slides. Okay, let's move on. Low-level programming bugs. So there are certain bugs that are specific to low-level programming languages such as C. Because C is more or less an abstraction of assembly. So C is a kind of platform-independent assembly, and C is a language that's very easy to compile to assembly. The reason for that is C has been a language that is designed for very old computers. It's designed to create operating systems. C has no memory safety, so C allows you to do raw memory access. And actually, sometimes you need that. So for example, when you implement an operating system, or when you implement a device driver or something like that, then actually you need like a language like C that allows you to do raw memory stuff. Other languages do not allow you to do that. For example, Java doesn't allow it. Python by default doesn't allow it. But when I say doesn't allow it, well, that means like by default. So for pretty much any language that's memory safe, there is like an extension that allows you to do raw memory access in some way, but at least not by default. It's not happening by default. C provides neither type nor memory safety, which means that you can accidentally switch between types in C. That might break stuff. And you can corrupt your memory in C, which might bring things even worse. And in C, memory is manually managed, which means that the programmer is responsible for allocating and deallocating memory. When you do that wrong, then things will break, and they will break pretty badly. Bugs may corrupt the memory of the program, so when there is a bug in your code, then the memory of your program might change in a kind of arbitrary way. And then arbitrary things might happen, and strictly speaking, what happens is undefined. So for example, we have this piece of code here in C, which declares a buffer with 4 elements, and then you're trying to assign something to the element with index 4. But a buffer with 4 elements has just indexes 0, 1, 2, and 3. So what happens when you assign something to element 4 of that buffer is totally undefined. Means when you have a C program, you do that in a C program, the results of that are undefined, which means anything might happen. And what usually then happens is that your memory gets corrupted. More examples. So, when I have a method here that gets, for example, passed a function pointer as an argument, and you have certain local variables like an integer disk quota, a boolean, a super user, and a file name and stuff like that, and a buffer, and then you're trying to access that buffer in that way, then it might corrupt contents of the other variables. And when you access, well, the buffer, when you write without the boundaries of that buffer, it will very likely corrupt the contents of those variables. So what might happen is that disk quota might change to another value. If super user equals false, might flip to true. The file name might be different, so it might point to a different file now. And also the function pointer, which is an error handler here, might point to another function. So, I have several programs now, and you're supposed to spot the defect in this code. So what is wrong with that C program here? Yeah?
May consume more inputs than size buffer.
Yes. So gets will read from the standard input until it encounters the end of line or end of file character. But when within the first 17 bytes of input that doesn't happen, then it will just continue writing to the memory, and it will write outside the boundaries of that buffer, and then it will overwrite other things. To understand what's happening here, we need to look at the stack layout. So what I have here is a stack layout on an ARM-based system. So I brought a small Raspberry Pi. And in general, not just on ARM, what usually happens is that you have a stack, and a stack has high and low addresses. And a stack starts growing from the high address towards the low address. So every time when you call a function in a C program, a new stack frame is allocated. The size of the stack frame depends on how many local variables this function has. And then when the function is called, what happens is that on the stack, there are two values stored. One is the return address. The return address points to the code where that function was called from. So by default, when you have a C program, for example, we have main here. And in main, you call readstin. So that's a sample C program. When you call readstin, what's supposed to happen is that readstin is executed. And after readstin is done and returns, then the execution is supposed to continue after readstin in main. So whenever you call a function in C, what happens is a new stack frame is allocated. And then at least the return address needs to be stored, because that determines where the code is supposed to continue when that function returns. What is usually also stored is a return base pointer, which is a register that points towards the stack, but that depends a little bit on the architecture. And then you have all your local variables on the stack, and then you have a stack pointer, which is a register that points to the last element in your stack. And then you have free stack space here, and here are the stack frames of the previous functions. So when your function would call another function, it would start allocating a new stack frame somewhere around here, right after your own stack frame. So what I already said is we have the return address, which is the address of the code that is supposed to be continued, where the execution is supposed to continue when that function returns. And one thing what I can do is I can try to modify that return address to make that program return somewhere else. So when you look at that code, where is secret called? Yeah? It's never called, right. That program will never call secret. The question is now, can we make it run secret? Yes, so we can smash the stack. We can try to find an input for that program so that it will actually then run secret. And I have prepared a small demo for you. Okay, that's our code. So we have secret, we have readstin, we have main. Main calls readstin, stin calls gets, and it has a local buffer of 18 elements. And secret is never called, and we can actually try to exploit that. And as I said, the compiler is already a static analysis tool, and the compiler already warns me, please do not use gets, it's dangerous. Yes, and now, but I'm going to do that now because that's a demo for a secure programming course. So we can, for example, now run that program. We can run with some input. That works fine, and we can run it with a longer input. Then it crashes here with bus error. What we can actually also do is we can run that thing in a debugger. They run. And we know that thing, well, 17 bytes of inputs are fine, so let's try 17 bytes of inputs. 4, 5, 6, 7, 8, 9, 10. Those are 10. Another 7 bytes of input, and now we start something else. So we start now with A, B, C, D, G. Well, that should be enough. And it crashes. And it seems to crash at an address called 4B, 4A, 49, and 48. So for some reason, the program tried to access address 4B, 4A, 49, 48. And we can check what that address is. So you all know what an ASCII table is, right? Can you try to figure out which ASCII characters correspond to those hexadecimal values here? Yep. Which one? 8. And let's see. Yeah, that looks good. Well, almost. Yes, so the output I get is for B, for A, for 9, for 8. So for B is a K, yes, and for A is a J, and for 9 is an I, for 8 is a H. Yes, so that looks good. So for some reasons, apparently our return pointer was overwritten with those characters. So what I can now try to do is, I can construct an input, and first of all, let's have a look at secret. So secret in that program is at address 1049C. So let's take the entire input, what I have here, up to H. See? And now I take the address of secret, where I would like the program to continue. And then it runs secret. So when I have a C program here with a buffer overflow, I can take control of the return address, and then I can make it jump wherever I want. And that's pretty dangerous for C code, and that's something that in general only happens for languages that do not provide memory safety. So when you have C code with a bug, like a buffer overflow, someone can craft a malicious input for that program and make it do other things. In general, there are two ways how to exploit buffer overflows. The first type is called code injection attacks, which means that an adversary builds some code he would like to run, gets that code into your program, and then tries to take over the control of the execution flow and makes that program execute that code. And there is a very old article that is named Smashing the Stack for Fun and Profit. And yes, I know that you might not be the biggest fan of, very old articles, but this one is really very well written. So I recommend that you take a look at it, because that was basically the article that explained how to exploit buffer overflows in C programs and how to build exploits. A lot of techniques in there nowadays do not work anymore because modern operating systems have countermeasures. But on the other hand, when you are not on a modern operating system, but instead you are on a platform like a microcontroller, that might even nowadays still have no countermeasures at all. So when you find a buffer overflow in a program running, for example, on the Arduino, then you might use exactly the techniques from that article to build an exploit and to take over control. And the modern way of exploitation is called code reuse attacks, which in general means, well, that's what we did here, because in that program we had code that we would like to run. It was simply, we were not allowed to run it, but we managed to run it by basically reusing code in a program. So modern exploits, they don't bring their own code, because bringing your own code nowadays is hard on modern secure platforms. But instead what they do is they try to reuse code that's already in the program in a way that was not meant, well, it's not meant to be used for. And in general, that's called return-oriented programming. So when you like to dive into the world of buffer overflow attacks, have a look at the article Smashing the Stack for Fun and Profit. And when you want to know how you can build exploits today that also work against modern platforms like the Linux operating system that is running on the Pi, with all security features, well, enabled, then have a look at this presentation that explains how you can build modern exploits that still work by reusing code that's already in the program. And we have one question. What programming language was that? C doesn't have a Boolean type. Yes, C doesn't have a Boolean type, but you can define your own Boolean type. And then that code actually works. You need a few define statements, and then it works. Yeah. Sorry? Or would you like to take a break? Okay, then we take a 10 minutes break, and I see you again at 16:50 for more C-level C bugs. We had a question. Will you publish the material for the assignments on Canvas? And if so, when it will be available? So yes, I will publish most of the material on Canvas. But actually, one of the things I'll also do is I will publish some of the assignments on the GitLab server. So I already said we have a GitLab server. Well, the student association was so nice to set it up. And the address is there, gitlab.snt.u20.nl. And what you all should do now is take some device, go to that website, and sign into the GitLab server. The reason for that is the GitLab server is synced with, well, can be used with your student's account, but as long as you never logged into the server doesn't know that you exist. And when I want to publish an assignment for you on that server, it will not work because the server has no idea of who you are. So I would now like to ask you, go to that GitLab server and sign in once with your student's account. Another thing is, I told you there is, well, you will work in teams of 2. When you go to Canvas, then you can go to the course and you can sign up to one of the assignment groups. So when you log in with your student's account on Canvas, go to this course here, and then I think somewhere around the people section you can actually sign up for an assignments group. And you should probably do that now, but is there anyone in the room who's currently still looking for a partner? Okay, then happy speed dating right after the course is finished. And try to sign up for your assignment group today, because when I publish the assignments on the GitLab server, I make sure that every group has access to their assignment, to their project repository. And for that, you need to sign up on Canvas. So I take the data from Canvas, your current, well, group, and I will then publish some of the assignments on the GitLab server, and I will link to that on Canvas. And I will also upload the slides from today, and I will also upload the video from today. Okay, I hope you're mostly done now. So what you have seen with memory corruption, that might not just happen on the stack, but it might also happen on the heap. So we also have data structures on the heap, and you can also corrupt the memory there. So for example, when you have struct bank account, there is a name as a buffer. When you overflow that buffer, then you might change your bank account number, and you're not supposed to do that. In general, on the heap, you do not have so many pointers to functions, but they exist too, so you might corrupt them, or you might use other methods for making the program do something it's not supposed to do. In general, corrupting the memory on the stack works much better for exploits, as long as stack canaries are not enabled, but I'm not sure whether we will come to that in that course. Okay, corrupting the heap. Yeah. So when you run when you put too much data into name, you will change the number. So you then get access to a bank account you don't have access to. I have another C program, for example, this one. Try to find out what does it do and where is the defect. Yeah.
Slash zero is not at the end of dest or whatever's in there, then string copy might continue. Or the target can be too small and then it doesn't fit in either.
Sorry, say again?
If the destination is smaller than the source, then you also have a problem.
Yes, so when the source contains more than 19 characters, then it will corrupt the memory because dest has only space for 19 characters. Another one that's a little bit more complicated, but similar. What's wrong here?
Because you've already placed a prefix in the buffer, the size is no longer right.
Be-
Because you're already using it.
So, well, the first thing is the string copy there is fine because the prefix is significantly not larger than buff. But what do you think? What's the problem?
The concatenation where you say buff and back, this buff has a certain length, and then you say, okay, I can use 20, but you need to remove the prefix from
No, it concatenates buff, which contains the prefix, and pass, which is not shown here, and stores it in buff. Yeah.
Isn't that size of doesn't calculate the length of a string?
No, size of buff is actually the size of the buffer. Yeah.
If we already have the prefix before, then the size of buffer is 20, so we pass the size of 20 if we concatenate both, right?
Well, that's
If we put a path like a path that is, I guess, 20.
the size of buff is 20. But what would be a correct value here as the third argument for string cat?
The size of buffer less the size of prefix minus the.
So when buff is of size 20, what's the correct value for n?
Just the remaining space, right?
Kind of. But so it says the size of the destination must be at least the string length of the destination plus n plus 1. So we would need to subtract the size of the prefix, well, the length of the prefix, and 1. So yeah, we have incorrect length argument here for the string cat. What's happening here? Yes. Yes. So C has a very special property about strings. So strings are always null terminated. So string is, well, simply represented in C as a pointer pointing to memory, where you find characters that are not a null byte. So string always stops at a null byte, which means when you have a string with 4 characters, you need a buffer of size 5. Because you also need to store the terminating null byte for the string. So when you want to store a string of length n, you need a buffer of size n plus 1. And that's why when you have a buffer of 20, you can only store a string of length 19. Because you always need 1 extra byte for the terminating null byte in C. We have more bugs in our C code.
What does read do?
Read is a low-level function to read stuff from a file descriptor. So with read, you can read from a network socket, from a file, or from something like that. So FD would be a file descriptor of a file that you have opened, or a network socket or something like that. And read will read from a file descriptor. Then you pass on like a pointer of where it's supposed to be stored. Then you specify how many bytes you would like to read from that file descriptor. Yes. Yes, but we are not reading a string here. Well, okay, well here, yes, it's last read. It's not null terminated, so you're right. So this read over here doesn't null terminate that, what we are reading. Here we don't need to null terminate that because it's not a string. We are reading an integer. Integers in C have a fixed length, so they are not null terminated. Yeah.
You're allocating for the variable that has been read and not the size of an integer. So if you read 0, then you malloc.
0 bytes, yes, but then we would also read 0 bytes from our file descriptor. So we read an integer here, then we allocate memory of size of that integer, and then we are trying to read so many bytes from that file descriptor. Yeah. Malloc can fill, yeah, that's one of the things. But what else might happen?
You're not checking the boundaries of what you're reading. So you can also read negative numbers.
Yes. So what might happen is that the read here will read a negative integer, so it will fail. So we can fix that by checking that the integer we've read that it's not negative. When the integer is negative, then we return with an error. And yeah, okay, we know malloc can fail, but when we are trying to read a string here, what's wrong? Yeah.
We should give it the pointer to the buffer, not the buffer itself.
But we're doing that. So char is the buffer is already declared with a pointer. Yeah.
There's a 1 byte overflow because of the not allocated for the null pointer.
Yes. So that thing is not null terminated. Now we make it null terminated. Do you still see bugs besides that malloc might actually fail? Yep. I am allocating my memory. How?
If length is maximum integer value, then you have an overflow.
Yes, we have an overflow. So what we're doing is we are reading length here. We are then checking that it's not 0. And then we're adding 1 to it. But when len is already at the maximum size of an integer in C, then this thing will actually overflow and we will pass a negative argument to malloc. So we have an integer overflow here. So we can check that. If len plus 1 is negative, here's fix. Okay, and yes, you already pointed out, malloc might fail. So we can check the return value of malloc, and when malloc failed, then we are also returning. Okay, there is maybe one more thing in the code that's not really a bug, but that can still be done better. Yeah.
I wonder why len is an integer and not an unsigned integer.
Len, yes. Well, you could make it actually an unsigned integer, but as far as I know, the argument for malloc is size t, yes. So I have no idea whether the size t is signed or unsigned. It could probably be unsigned. So yes. So we need to check for that here. Yes. That's one more improvement. Another improvement is that the memory returned by malloc is by default uninitialized. So one way how to do it better would be to use calloc, which gives you initialized memory. So as you see, getting C done right is really hard. Another thing is, where's the bug in this code? Yep. So short might be a single byte. And what else is a property of short? Yeah?
If the input is larger than the length of a short,
Yeah.
the length might wrap around and become smaller. So then the check will succeed, even though the input is bigger.
Yeah. That's correct. So short will overflow, probably overflow at 127. So when len overflows, like string len will return 128, then this one will always succeed, and then that will be executed. So in C you have like an implicit conversion between certain integer types, and that can be a big security issue. Because also in C the size of certain types isn't really defined. So depending on which platform you're on, int might have a different size. So sometimes it's 32-bit, sometimes it's 64-bit. And that can create a lot of issues, especially problem with those issues is the size of an int doesn't usually, well, doesn't differ from execution to execution, but may differ from platform to platform, which means when you're coding something on your 64-bit computer, and then you try to run it on a 32-bit machine, it may behave differently. Okay, I have another thing. Now it's getting a little bit more difficult. We are trying to copy a URL. Yep.
In the way you copy the URL, it doesn't check for the null byte, so it can keep going on longer than the string name.
So, okay, we don't have any handling for null bytes here. That's correct. Yeah. So what kind of? But it will terminate the copy operation at another point. It will not stop at a null byte. But when will it stop?
When it reaches a forward slash.
Slash. Yes. So it will stop the copy operation when it reaches that slash here. But there might be no slash in the URL. So then it will just go on till it hits the next slash, which might be somewhere outside the boundaries of that buffer. And I have something very beautiful for you. And that's actually an entire program, so you can all now try to compile and run that on your computer. And when you're lucky, then your compiler will tell you how you screwed up. Or can you see it? So who sees the bug? Seems to work well, right? %s. Nice, isn't it? So that's a format string vulnerability. So the first argument for printf is always a format string, which may contain certain escape sequences. So for example, when you try to write a program that prints hello someone, then you do it that way. So %s says that the first argument after the format string is supposed to be a string and it should be printed as a string. I could also replace it, for example, with %p, which says that the first argument is a pointer that is supposed to be printed. And then it doesn't print hello Eric, but instead it prints hello, and then the address of where Eric is stored in the program's memory. And that can also be a very nice way of creating a security relevant bug, because it will allow an attacker in general to dump memory contents of your stack. And it might also allow an attacker to modify your stack, because there are also arguments for printf that will make write something to the stack. For example, the number of characters that were printed up to now. Okay, what's the problem here? Yeah?
Free can decode twice on pointer or something.
Yes, we have a double free. So we'll try to free memory twice, which might corrupt our heap, because we are supposed to call free only once for everything we've allocated. What's happening now? Sorry? Yeah, you're using memory that you have already freed. So here we have a call to free pointer, and then we're using that pointer here. So that will print, well, it will use memory that has probably already been allocated for something else. So the problem is here we are checking if an error occurred. We are setting abort to 1. We are freeing that memory that we have allocated here with malloc. And then later on, we are trying to actually use that memory again. We are not supposed to do that. Okay, it's getting probably boring. So one last thing for you. And this program is supposed to write something secret here to a file that only the current user is supposed to see. Maybe I should tell you what fchmod does. Fchmod changes the permission of a file, and when you call it like that, then it changes the permission of the file that only the current user is allowed to read and write from it. No one else, so no one from the same group, and no one else is allowed to read or write or execute that file. So the permissions of that file will then be just read and write for its owner, and nothing else for anyone else. In Linux, that's equivalent to saying chmod with permission 600. Yep.
I'm not sure, but the return code, I guess, should be negative in case it fails.
Depends. Well, it doesn't have a main page, it's your own program, so you can make the return code whatever you like. But yeah, 1 or -1. Apparently 1 is quite common as a error return code in C. Yeah.
You can make the temporary file in France. Then if it opens it, you have the privilege to change the privileges.
So I am opening a temporary file. Then I'm doing what?
Well, if you create the file beforehand, before executing the program, then it will succeed in changing the modifier.
Yes, so what's the security problem here? assume that you're logged in as a different user on the machine that program is running on.
The text is secret, right? So
Well, okay, let's ignore that. So let's assume here is something really secret, not
Yeah.
just a static text.
So, what you can do, I think, is create the asecret.txt and then execute this program. And because you own that file, the change modifier will work.
Yes, so someone could already have created that file, but it's now owned by under a different owner. Yeah, so that might happen. Even worse, what can actually happen is that the file isn't there, and actually in fopen you can also pass flags to fopen that make sure that when the file is already there, fopen will fail. But we are not doing all our file operations here in an atomic way. So here we are calling fopen, and here we are changing the permissions. And between here and here, the file is already created, but readable by another user, which means that when you're fast, then you can wait until another user has created the file here with fopen. Then you open the file, because now you're still able to open that file. Then the other user changes the permission so that's only read and writable by him. Then you write something secret into the file, but you're still holding the file handle. File permissions are only checked at open time on Linux, not while the file is open. Then as another user, you can read the contents of the file. So the special thing about that bug here is that may happen in any language. It's not specific to C. All the other problems that you've seen before are specific to C or C-like languages. So, well, C++ is pretty much backwards compatible to C. So everything what you've seen before, well, that might happen with C++ as well. But this one is kind of more generic. Okay, how to fix that? Number one, don't use C. When you have a project where you need a lot of security, C could be a very bad language. So when you have a chance of avoiding C, avoid C. Next thing is manually check your code. Even better, statically check your code with a tool. For example, there is CPP check that will discover some of those bugs, and you can examine your running code using Valgrind. So let's come to your assignments. Assignment number one. Take the code from the slides with defects. Turn that code into full programs, and then check which bugs are found by either the compiler, you can use GCC or CLang, CPP check, which is a generic tool for checking C code, and Valgrind, which is dynamic analysis tool. So Valgrind will run the bug, and it will run the code, and it will instrument your code, and it will probably find a few of those bugs here. Assignment number two. We will provide you with a vulnerable program in C, and we will publish that on the GitLab server. And your task is to fix the program and also document what you fixed. So do not just submit the fixed program, but also say what you changed and why you changed that. Assignment number three, that's optional. So when you would like to get an excellent, what you do is you look for an open source program that is still actively maintained. That's a little bit popular. So actively maintained means, okay, let's say there has been development in the last 24 months. So commit, you release, something like that. It's a little bit popular, so let's say when it's hosted on GitHub or GitLab, you have at least 10 forks, clones, whatever, stars. And it's written partially in C, and you find a security weakness in it, and you report that to the developer. Okay, let's see how we continue. So next week we will run a lab session where we will help you a little bit to play around with those tools. So next week we will focus a little bit on CPP check, on Valgrind, what they can do, how they can be used. And for the assignments, I think it's quite fair to say you have always up to the next lab session to submit them, which means that you will submit those assignments until now in 3 weeks, because in 1 week there is a lab session where you will get support for that, and in 2 weeks thereafter you should have submitted that, because then the next lab session starts where will we start, in which we will start Rust coding. And for the bonus part, actually get a little bit more time. So try to get it done as quickly as possible, but just in case you're not done with it in 3 weeks, you get a little bit of extra time. And I will also publish that on Canvas. Any more questions? No? Then have a great evening and see you again in 1 week.